the last lecture, we started working with the Markov processes. We introduced Markov processes without self-jumps, just for simplification that will become obvious today. And we looked at the property of detail balance and the condition for detail balance called Kolmogorov criterion, which will come back useful later on in the course. But now we turn to large deviation theory again, and we will do for Markov processes exactly what we have done before for simple frequencies. Okay, there will be many things in common with what we have done before, but of course there will also be things that are not in common, and Markov chains are more difficult. So before, remember, we were considering a symbol in an alphabet, and we were looking at the frequency of the symbol after n samples of the symbol. Was defined as the sum from 1 to n of the occurrence of the symbol, okay? Whether n was equal to omega, okay? This was with the independent identical distributed symbols. Now we move to Markov processes. We are talking about states in a state space, and we are more interested into transitions than single realizations of a symbol. So what we are going to look at is counters. We could look again at the empirical, this would be called the empirical density here for Markov processes, but today we are going to work instead on empirical frequencies of jumps. So the observable we look at is not of this kind. We could be considering, and there are many interesting results for that thing in for Markov chains also, but we will look at a two-state object, which is just the sum from n1 to n delta, that omega n is in omega, and then we have delta omega n minus 1, it was in omega prime. So this is basically the number of times that the transition from omega prime to omega has been performed. Okay? And of course the sum over omega prime of x omega prime is equal to n, which is the total number of jumps. Okay? We want to, and let me also aggregate all of these variables in so the idea is we want to find the joint probability for all of these counting variables. So that's what we're looking for, is the probability that xn take values n. Okay? If we manage to calculate this, we are doing a little bit better. What we know is the probability of the trajectory, right? That's the starting object. The trajectory, this we called level 3. I don't actually like this numbering of large deviations, but people use it. In principle, what we would like to know is the statistics, the probability of an arbitrary observable, like the number of times one particular transition has been performed, or the number of times that we went out of a certain domain, or the number of times, and so on. And that would be called a level 1 observable, because it's just one observable for which was the marginal. in fact, apart from specific cases and systems, it's very difficult to attack that kind of questions. So what people have been looking at is large deviation functions for joint observables, and in this case, when we consider the probability of all of the possible transitions in either direction, then people call this sometimes level 2.5 large deviation. Level 2 would be large deviation for the empirical densities, for example, or large deviations for the currents, which are antisymmetric observables. Level, I guess this 2.5 has to be understood as just a slight improvement on this probability, but not so great. Still, we will be able to calculate this and actually use it for some purposes. So it's not completely useless to calculate this thing. So let's go back to our probability. So how do we calculate this probability? Well, x will be equal to sum over all possible paths of length n, the probability n, and then there is a delta that keeps track of x. That's just the definition. We have an explicit expression for the probability p, which we write in this way. So, well, I remind you that the probability of the trajectory is just the product. Is the okay, and then there is a initial probability that well, we can write p omega 0, okay? So now, consider this. Consider two given states, omega and omega prime. Now, every time that this transition is performed, you get a factor rho omega omega prime. And you obtain as many as these factors as the number of times this transition has been performed, which means that this rho, this probability, will be multiplied by itself by an amount of time which is x omega omega prime of n, by definition of x, right? So we notice that we can write this as sum probability. Well, the probability now is product over omega omega prime, rho omega omega prime to the x omega omega prime and delta x and x. Okay. So now this is very nice, because this expression depends explicitly only on the empirical counters of times that the transition has been performed. So we can act with the delta, and just this can go out of the sum, right? Because it's not affected. So this will go like prime rho omega omega prime to the x omega omega prime and then we have a sum over all trajectories of length omega delta x and x. Okay? So this is a very nice result. Let me comment briefly. Again, this is a term that depends on the probabilities explicitly. And what is this? This is a purely combinatorial term. It doesn't include the probabilities, and it's just some integer number that counts something. What does it count? We will say it later, but as we saw before, this probability, like in the case of the coin, is made of an energetic part and an entropic part, a purely combinatorial part. So this one, sorry, we don't have the n now, we have explicitly evaluated x on the values that we want to compute. So now we have to turn to that number. So we have to evaluate the sum over all possible paths delta x and x. So think about this. This is the number of paths that jump a fixed number of times across each of the transitions. So you fix the number of times that you jump from 1 to 2, 2 to 3, 3 to 2. You say, I want to jump 7 times, 5 times between these two, 8 times between these other two, etc., etc. Now this number is going to tell you how many ways of doing this trajectory there are that perform, that give those numbers. So we can represent this as follows. Suppose for each x omega omega prime, let's draw one arrow from omega prime to omega, and let's give it a direction. So for example, if this is 3, we draw 3 arrows like this, okay? Of course, we also have omega prime, omega. If this is 2, we draw 2 arrows like this. And so on, we do it for all omega, omega prime, okay? So, in the end, so let's say that my state space is like this, we will have something like maybe this is 2 times, this is 1 time, and then we have 1 like this, and 1 like that, and probably, it's not balanced, so we need at least here, no, it's balanced. So, we drew 1 arrow, directed arrow per each number of times that the trajectory performs this particular jump. And notice that because we are going to consider, for simplification, a trajectory that ends up in the same state where it started from. Okay, this is just a smaller assumption that doesn't play any role, because if it doesn't end up in the initial state, the final part of the path until you get back to omega 0 will, in the long time limit, will not play any role. But let's stick to this. So in this case, we have that these numbers must be balanced, meaning that the number of times I jump into an out of a omega prime must be equal to the number of times I jump into an omega prime. Okay, but because the trajectory of the Markov process is continuum, so you never lift the pencil. And so, if you get back to the initial state, you must have as many arrows that go in and as many arrows that go out. Now, this object here is called a balanced digraph. Okay, so we call it balanced digraph. G of x, because x is the input data that gives us the number of arrows. Okay, and now this number here is the number of different paths that I can draw on a balanced digraph starting from some state omega 0 and going back to the omega 0, such that I use each arrow at least 1 time. Okay? So this is a very well-known problem in mathematics, in graph theory. It's called, so this will be called Eulerian trails. And there's a theorem called the best theorem, after the name of the discoverer. It's not the that tells you how many of these Eulerian trails there are. So, in particular, the best theorem states that number of Eulerian trails on this graph Gx, and now I need to be careful, is equal to factorial. So the number of paths that I can draw without lifting the pencil on a balanced digraph in such a way to use all of the errors at least once, no, just exactly once, is given by, there's this product of the factorials of x omega minus 1, where x omega is the out degree, or also the in degree, well, it's this one, is this also here. Okay, so this x omega is the out degree of each node, so it's the number of times that you pass enter into a node, or also that you exit by a node. And now t omega 0 g of x, this is the number of spanning trees that have root in omega 0. So what is a spanning tree? Let's move here 1 second. If you have a graph, then a spanning tree is a maximal subset of edges that does not contain any cycle. Okay, this is a spanning tree, this is a spanning tree, this is a spanning tree, etc., etc. Okay. Now, if we have a balanced digraph, then the spanning trees will have, let's say that the root is omega 0 now, then the spanning trees will have to be oriented into omega 0. There's one unique way to go from any state to omega 0 via the edges of the oriented spanning tree. So, this is the number of spanning trees with root in omega 0 that this digraph admits. And how do we prove this result? I won't prove it in the general case. I will give you references for it, but let's just give an idea of why it works. So let's go back to this example here. So let's take as root this one, omega 0 is our root. Okay, so we fix one spanning tree, okay, with root in omega 0. Let's choose this one. This is a spanning tree, okay. Now the spanning tree has the property that each vertex but the root has one outgoing transition edge, okay? So each one has exactly one, okay? So we define these particular edges here as the last edge that we use to exit this particular state, the last time that you visit the state. So you perform your trajectory and you always go around other edges. The last time that you visit this particular state, if you have used all the other possible edges out of it, then finally you use the red edge of the spanning tree. But you're not allowed to use the red edge before, okay? So now, we fix this one spanning tree, and now we start from omega 0. How do we choose? We can choose any particular transition out of omega 0 at random. So we can choose out of how many we have x omega possible transitions. Yeah, sorry, this is a small. If I remember well now, we have a delta omega 0 just for the initial state, because we have we can choose any particular transition out of omega 0. Okay, so then we go to this other state. We can choose how many. We cannot choose the red one, so we can choose any transition out of it in any other direction. So now we have performed, for example, this. We choose this, okay, and we have a certain number of choices. Then we are here. We can choose any particular transition that is not the red one. So we have this. Then we are here, we can choose one of these. Then we are here, we can choose one of these, and so on. Up until, for example, we end up, probably this is not balanced, I don't know. Well, suppose at some point I get back to this state here, and I've used all other possible edges, then I have to perform this transition, okay? And so on and so forth. This way of accounting for path is such that you cannot perform the same path. You do not count the same path twice, because each spanning tree and each choice of the other edges will select one unique path. And also, the other thing that one has to check, and this is not a so easy part of the theorem to be proven, you have to show that you don't go back to omega 0 before having used all of the edges. Okay, we have to use all of them. So this technique, you can try one simple example, will not make you go back to omega 0 to close definitely the path until you use all of the edges. And the idea is the following. If you did go back to omega 0 but didn't use all of the edges, you must have left out a cycle out of your path. But if you left out a cycle, because a spanning tree cannot contain a cycle, it means that you went out of a state by the spanning tree before using one other edges which did not belong to the spanning tree. That's more or less the reason. So if suppose I got back to omega 0 before using these transitions here, okay? Well, omega 0 now is here. I did my Eulerian path, and I went back to this, okay? So now maybe this may be red, this may be red, but definitely this cannot be belonging to the cycle, which means that at some point I used this transition here before using this one, and I wasn't allowed to do this. Okay, so this is a way to think about this theorem. So now you see the choice of the tree is like where it comes from, and these factorials, this is factorial. These factorials here come from the different choices that you have to go out of a state, but via the edge belonging to the tree. Okay, so it seems like we have it. We have a little thing to be taken care, because so now our sum of omega and we have said this is equal to the Eulerian trails g of x. There's one little thing to be taken care of here, is that when the Eulerian path problem is formulated, the idea is that the different transitions are distinguishable. So it makes a difference if you take this particular edge or this other particular edge. But in our case, instead, it doesn't matter. It's just a transition is being performed and not that particular transition. So the solution is given by that one, but we have to divide by all the possible choices of number of transitions. Okay? So now we have this nice expression here. It's P omega 0 Gx, and then we have all these factorials. Okay. We are almost where we want to go, so we can put it all together with so this is just the entropic part of the expression. Let's put it together with the probability part. So we have the probability is n equal to x is equal to and then all of these thing here. Okay. So now notice we are going to look at large deviations, of course. So we look at empirical frequencies defined as over n. But then this guy scales with n. These we can use the Stirling approximation for the factorials. So these will also grow with n log n, also n log n. What about this guy? Do we know that this guy will not grow exponentially? The answer is yes, and it comes from this other theorem in graph theory, because so the number, this is another very nice result in graph theory, that is called the matrix tree theorem. Which states that you can compute the number of spanning trees of a graph taking the determinant of a suitable matrix. And the matrix is this one. It's just you create the matrix T omega omega prime, which is x omega omega prime for omega different omega prime, and minus x omega for omega equal omega prime. So it has it's a stochastic matrix because the columns add up to 0. And so then we can write the T omega 0 g of x is equal to the determinant of T from which I removed the omega 0 column and row. Okay? So this is also another very, very nice theorem in graph theory, connecting graphical properties, trees, number of trees, to matrix, linear algebra properties, matrices. And it tells you that this number will be the determinant of T. But the determinant of T will contain x up to a maximum number multiplied, well, basically the x will be contained up to powers of omega, the size of the state space, because this is a omega times omega matrix, right? It's a square matrix whose dimension is how big is the state space. So the determinant of this is actually minus 1 because we removed one row and column. Okay? So this x here will not be, so that this will grow with n. When we take the frequency, this will go like xn to the omega, so this provides a polynomial contribution and not an exponential one. Okay? So if you lost your mind, it's time to refocus. Let's forget about all these graph theory things. Let's just get to the result. The core point is we started from a probability of a trajectory of length n, and we want to find a probability that certain observables take certain values, and this x observable is just the collection of x omega, omega prime for omega and omega prime in omega, which count the number of transitions that the trajectory has performed between omega prime and omega. And we see that the probability of these observables is given by two factors. One is the energetic factor, let's say, the one that depends on the probability. So it's just product over n2 space, the probability of the transitions to the x omega omega prime. And then there is a combinatorial factor that depends on the number of possible paths that have given values of this x. So this is a combinatorial, and we calculated it, and was given by, so this is times t omega 0, and then there was product of omega x omega minus 1 plus delta omega omega 0 factorial, and then product over any two states of x omega omega prime factorial, where x omega is just the sum over omega prime x omega prime omega. So basically this is the factorials of the out and in degrees of each of the states. These are the factorials of all the possible transitions between any two states, and this t omega 0 is the number of spanning trees. But we saw, now we are going to look at large deviations, large n, and in the large n limit this will grow exponentially, this will grow with Stirling also exponentially, and this is just a polynomial growth, so we will be able to kick out. So again, now large deviations, we take empirical frequencies, omega omega prime of n is equal to x omega omega prime n over n, and now we look at the probability. So the definition of the rate function, as usual, is f of all of the x is equal to the limit minus the limit for n to infinity 1 over n logarithm of the probability that the x big of n take values n x. Okay? And this is exactly the same calculation as we've done before with the relative entropy, because we will have x log x minus x log x minus x, etc., etc. I don't do it explicitly, you do it as homework. You obtain sum over omega prime, x omega prime, logarithm x omega prime over rho omega prime x omega prime. Okay? So this is for Markov chains. Okay? And this is called Sanov theorem for Markov Okay, look, it is indeed very, very similar to the sum of theorem for ID, but in that case, we had that the rate function was sum over omega, x omega log x omega over rho omega. So that was a relative entropy of x omega with respect to rho omega. Okay. And so the idea is, suppose that instead of looking at a Markov chain, we just looked at a variable omega that takes actually a couple of values. Okay, we can split it in omega in, let's say, instead of omega, let's say alpha prime. Okay, we can just re-index things with two indices. Then this would be alpha prime as alpha prime, alpha prime, and it looks very much like this, but it's not the same, of course, because this is not a relative entropy because of the appearance of x over there. See? So, is the sum of theorem for Markov chains, it is not just a rewriting of the sum of theorem for ID in the case of two state variables, because there is the effect of this guy, and this guy is provided basically by the continuity of the trajectory, the fact that you cannot lift the pencil when you jump from one state to the other. Okay, so you're not just sampling transitions at random, because the next transition is conditioned on where it was before starting, and this conditioning shows up here. Okay, so now, this we called a level 2.5 large deviation principle. Why 2.5? Because it's really not such a great improvement with respect to knowing the full probability, the full trajectory, but it does allow us to derive some results which regard observables at the lowest level of this hierarchy, which is level 1, which is the observables we're interested in. So, and in particular now we will apply this result to a current. So what is a current? Let's go here. So instead of looking at all possible transitions between any two states, we want to look at an observable phi of n defined as a linear combination of all possible transitions. So we write it as phi dot x of n. So now this phi is a vector, is a linear combination of the x of n. Defined as so there will be some coefficients, omega prime, and x omega prime. Okay, so this is a level 1 observable, and in theory, if we wanted to calculate the rate function of this object, we would have to take marginals or the contraction principle that we explained before, starting from the level 2.5 and contracting up to the level 1. This is prohibitive, but we can still do something. Actually, I'm not interested in any possible linear combination. I'm interested in currents type observable, which means that we take these combinations to be anti-symmetric. Okay? So we're always considering the number of transitions from omega prime to omega minus the number of transitions from omega prime in some linear combination. Okay? So now the contraction principle states that now we take the empirical current as B phi n over n, take the large deviations as usual. So the probability that this guy takes values phi will grow like e to the minus n some f of phi, where the rate function f of phi is given by the contraction principle. We studied it before. It says that f of phi is equal to the infimum of f Markov chains of x over the constraint x equal to phi. So this is this constraint here. We want the current to take that particular value, and let me write something like this. 1x equal to 1 is just a notation for some over omega prime, x omega prime. Okay? Sorry. Okay? And phi x is some omega prime x omega. Okay? So this is what the contraction principle says. By the way, f Markov chain of x, we just calculated it, is sum over omega prime, x omega prime plus omega x omega prime over rho omega prime x omega prime. Okay? By the way, I didn't mention it, but you can do it as an exercise. Prove this function is convex. Okay? And it can be shown that any such infimum with linear constraints of a convex function is a convex function. So all of these current rate functions are convex and do not suffer from that problem I talked about before. Okay, so I guess you can also see why this infimum problem here is so horrible, no? Because it's really, you have linear constraints, you can deal with the constraints, put in maybe Lagrange multipliers, but then, because the functions are convex, we can take derivatives, but when you take the derivative of this and set it to 0, you will have some linear terms, but you will also have some highly nonlinear things here. So solving this equation, even if it's convex, solving this equation directly is not feasible. So what we want to do is to at least find some inequalities that constrain this function and tell us something about it. And in particular, because this is a minimum, an infimum problem, it means that this will be less than any evaluation of this function which satisfies the two constraints. Okay? So instead of taking the infimum over all possible x, the infimum here is over all x. Okay? We can satisfy this constraint. I can just plug in any value of x, right? Which, as far as it satisfies both constraints, and I know that what I get will be bigger than this, okay? Because this is an infimum. So I can just plug in some x of phi, where x of phi is such that satisfies the two constraints. Okay. So now I will just propose one such solution. Which is x omega prime of phi is equal rho omega prime plus rho omega prime plus rho omega prime rho omega half plus phi over phi rho. I will tell you 1 second what that is. Okay, where phi rho is given by so this phi rho is one reference value, is just the expected current, okay? Because it's just the linear operation that defines our current evaluated on the steady state, on the stationary measures, okay? So this is the steady state value of the current. Then we have this particular antisymmetric combination and this particular symmetric combination, okay? And we have to check that it satisfies both constraints, okay? So now if you take the sum over all omega and omega prime here, sum over omega gives 1, sum over omega prime gives 1, sum over omega prime gives 1, sum over omega gives 1. Okay, so this is going to be 2 over 2, 1. And this, when you take sum over omega and omega prime, they cancel out because it's antisymmetric, okay? Then we have to check this constraint, but again, this part will vanish because now this phi is anti-symmetric. And when you act on this, you obtain precisely twice the value phi rho, okay? So this will cancel and it gives you phi as we wanted, okay? So this is a good candidate. We can just plug this particular answer into here. We go here. Before doing that though, let's do a little few considerations more. So from this particular solution we can also compute x omega phi, which is sum over omega prime x omega prime of phi. Well, you can do the calculation. When we sum over omega here, we get 1, so it gives you rho omega prime. This, when you sum over omega, this is the stationary equation, so this gives you rho omega prime again. So this will give you rho omega from the first part. And when you sum over omega here, you get this sum over this minus this, but this is the stationary equation, so this is 0, okay? So x omega is rho omega, okay? Which is nice, because when we plug into our expression for the rate function here, when we plug x of phi here, this guy here becomes rho omega. And this is very convenient because this was what was causing problems. You see? Also, we noticed that when we evaluate x omega prime on that particular value of the current, of phi rho, we get rho omega prime, rho omega prime, which will be useful. Finally, let's use this expression here. We can use the logarithmic inequality. Log x is smaller than x minus 1. And this leads us to the following, that f of phi is smaller than h of phi, where h of phi is defined as 1 over omega prime square minus 1. Oh, now, okay, so now we have this bound on the rate function of the current by this h, which is a quadratic function of the x, but x is linear in phi, so this is a quadratic bound in phi on the rate function. Okay, we could express it explicitly, we don't do it. What we notice is the following important properties. Well, I remind you that phi rho is the stationary or most probable value of the rate function. Okay, in fact, it's where we have that phi rho must be equal to 0. Okay, and also that the second derivative of phi rho must be equal to 0, because that's the most probable values. We have seen this at the beginning of the course. And we have that phi second of phi rho is equal to 1 over variance of the current. Okay? This also we saw at the beginning of the course when we discussed the Legendre transform. Okay? No, I will just erase quickly. I don't need much space. So we have that phi at the most probable, the rate function is 0, the first derivative is 0 at the most probable value, which is the stationary value of the current. And this is 1 over variance of the current. And then we have this expression for h. I erased the expression for x, but you can show easily that h of phi rho is 0 when we evaluate. Let's see, that was because f omega prime of phi was the symmetric part plus phi over phi rho antisymmetric part. Over 2, and now you have, when you evaluate on phi rho, this gives you 1, but then this cancels with this, and you get rho omega prime, rho omega prime. Then you plug it in here, and you obtain this. One of these cancels with one of these, and then you get 1 minus 1 equal to to 0. Okay? You can also do it as an exercise, that H prime at that particular value is 0. And then we have that F must be less than H of phi. But let's look at the vicinity of phi rho here, because at phi rho this is 0 and this is 0. The first derivative is 0 and this is 0, so for this inequality to hold in the vicinity of phi rho, it must be that the second derivative are bounded by the same inequality. Therefore, we have that the second derivative at phi rho must be smaller than the second derivative of h at phi rho. But this, we said, is one of the variance. And this guy we can calculate explicitly from this expression. I won't do it explicitly, but what you obtain is that h second of phi rho is equal to 1 over 2 phi rho square, and then sum over omega prime okay. And now this guy, let's call it sigma, maybe. Okay. What does sigma mean? This is a very interesting object. We could interpret it as a measure of distance from equilibrium, because if detail balance holds, then this is 0. This quantity is always positive. So it is positive and it is vanishing if and only if the system satisfies detail balance. Okay? Sigma is non-negative, and it is 0 if detail balance. Okay? So this is a good measure of irreversibility. Okay? Because it is only 0 at equilibrium, and otherwise it is always positive. Okay? It is like entropy production, like the second law of thermodynamics that states that the entropy of the universe never decreases. So this could be interpreted as a sort of entropy rate. And therefore, in the end, putting it all together, we obtain that the variance of the observable with respect to the average stationary value square must be bigger than 1 over 2 sigma. This is called thermodynamic uncertainty relation. It's an important result. It's quite recent. I will give references in my notes. And let's look at it. It says basically this quantity here on the left measures the precision of an observable phi of the current, because the variance over in a way, a balance between precision and dissipation. And it's a nice result because you can obtain it without actually knowing the rate function of the current. This is it for today. But not for you.